I think I am live now, and I hope the audio is fine. Can someone in the chat confirm? Hello. So, hello everyone. Today I would be discussing Atcoder ABC rounds problem, the contest which has just ended. And because there is a code forces round at 8 p.m., 8:05, so I have a hard stop at 8, and I will stop and I may try to create a one more stream tomorrow to discuss the remaining problem if required. So let's get started. Let's start with the first problem. The problem name is 2023 where 3 is typed off. And problem statement says you are given a string S consists of lowercase English letters. S is okay, voice is echoing. Let me check. Is it still echoing now? PC source. Okay, one second. Test 1 2 3. Test 1 2 3. Okay, I think the voice is relatively better. Yeah. Okay, so I will start. Okay, the first problem statement says you are given a string S consists of lowercase English letters and digits. S is guaranteed to end with 2023. Change the last character of S to 4 and print the modified string. Constraints are S is a string of length 4 200 and everything is fine. Let's look at sample first. Like hello 2003 becomes hello 2004. World Tour Finals 2003 becomes World Tour Finals 2024. 2023 becomes 2024 and so on. Like we don't have to replace all four threes with four. Like for example, 2023 and 2023 becomes 2023 and 2024. So I will jump on to my code for this one. So here I am taking S as input, then I am replacing last character with the 4 and printing it. And probably I will move faster to the next problem in the interest of time. And if someone wants to ask some question on it, I can take it again. The second problem says tetrahedral number. We are given up integer n and we have to print all the triplets of non-negative integers x, y, and z such that x plus y plus sum of x plus y and z is n in ascending lexicographical order. And we are also given the definition of lexicographical order for non-negative integer triplets. A triplet of non-negative integers x, y, z is said to be lexicographically smaller than x, y, and z if and only if one of the following conditions are. Either x is less than x dash, or x coordinates are equal and y coordinate is less, or x and y coordinate are equal and z is less. And if you look at the constraints, like n is up to 23. So like one idea to do over here is we iterate on all the possible values of x, y, and z between 0 and 21. In the increasing order, we take x in the outer loop, then y, and then z. And if some of them is less than 21, we print them. And this will also ensure that this order is maintained because we are outer loop is in, we are first printing all the values with equal x and y, then we would be printing x and z. And I will also go through my code for this one. Code is pretty much I take n as input, then I am iterating a for loop on x, then a for loop on y, and then a for loop on z with the condition that x plus y less than n and x plus y plus z less than n. And I am printing x, y, and z over here. So like A and B were mostly about implementation problems, like do whatever has been asked in the problem. Moving to problem C now, it's a bit interesting. Long tracking. Takashi has created a game where the player controls a dragon on a coordinate plane. The dragon consists of n part numbered from 1 to n, with part 1 being the head. Initially, the part I is located at coordinate I, comma 0. Process Q queries as follows. 1C, like if the query is of form 1 and C, we should move the head by 1 in direction C. Here C is one of RLUD, which represented positive x, negative x, positive y, and negative y direction respectively. Each part other than the head moves to follow the path in front of it. That is, part I moves to the coordinate where part I minus 1 was before the move. Find the coordinate of part B if the query is of form 2 and P. Like it's more like a snake and ladder game which we used to play when we were small in the Nokia mobile. And like if we look at the sample over here, right? So in the first query, like first the head is at 1, then second part is as 2, 3, 4, 5. And then when it asks to move up, like 1 moves up, 2, 3 and follows 2, 3 and 4 follows the position of 1, 2 and 4 back. So it moves like this. And then it's asked to move first to the right and then to the down. So if one moves to the right, like this would be 1, 2, 3, 4, and 5 would be the coordinates. And if one moves to the down, like this coordinate would be 1, 2, 3, 4, and 5 again here. So like here you can see like 1 and 5 are at same position, 2, 3, and 4. And then when one is asked to move to left, like the head from here will move this side. So like 1 comes here and like 2 follows, like everyone follows the same direction, 2, 3, 4. So like that's how it will look like. And if I have to like visualize like how does this works, like let's say like the snake is like this first, and if we have been asked to move snake down, right, then this place becomes 1, this becomes 2, this becomes 3, this becomes 4, this becomes 5. And then we have to if move left again. And this becomes 1, this becomes 2, this becomes 3, this becomes 4, this becomes 5, and yeah, pretty much. So if we notice over here, like what are the changes over here? If we maintain this position as a cyclic array, like where this is 0, comma 1, if we try to list down the coordinates of all the points, in the first case it would be 0, comma 0, like this. Sorry, not 0, comma. Like the starting would be 1, comma 0, 2, comma 0, 3, comma 0, 4, comma 0, and 5, comma 0. And when we move down over here, like the coordinates become like 1 moves to, like if we are moving downward, then 1 becomes minus 1, comma 1, like 2 comes at this position. Like these are the coordinates when you move down once. And then let's say if you move to the left once, then the coordinates are like coordinate of 1 changes and it becomes 0, comma minus 1, and everything else follows the rest of the pattern. And if you compare any two consecutive arrays over here, like if you look at this, if you look at this array and this array, you will notice that like first coordinate is random, this value is random, but rest of the array remains the same. So what we can do is, like, instead of changing the position of all the coordinate at once, we can maintain a new position, like where, like denoting where the head is, and we can try to change the last coordinate where the point is. So for example, if I look at it again, like if I look at my original example again, 1 comma 0, 2 comma 0, what I can do is I can move my head to a different, if I assume it as a cyclic array, what I can do over here is like 1, 2, 3, 4, 5. Yeah, like initially the head is here. What I can say is that next time the head is here, and I just replace this position by a new coordinate of 1, which would be, if I am moving down, the new position would be 1 comma minus 1. Then if you notice over here, this is the coordinate of the head. This is where 1 is, 2 is, 3 is, 4 is. And next time when I have to do the same thing, I find where the last index is. In that case, moving again, the last index would be at this place. So I erase the value at here. And if I am moving left, the new coordinate becomes 0 comma minus 1. And I say my head is over here. Then if you look at it in this terminology, like head is here, like the next coordinate would be here, and like it's more like, so like here it would be. So the way to do it would be, you maintain a array listing down all the positions. Every time whenever you want to find a new position, you find where the tail is. Like let's say if the tail is here, then you just write the new position of head here and assume that this is a cyclic array. So if you go to, like if you have index 5 and total length is 7, then 6, like 7 just corresponds to the first index 0. Like that was the main idea. Like this way you would be able to maintain all the updates in order 1 over here. Like instead of moving every point over here, you maintain a pointer where your head is. And like if I jump on to my code for this one, okay, this one was C problem. Like I created one auxiliary method given a coordinate and the type of character, what should be the new coordinate. So if it's right, increment x, if left, decrement x, if up, increment y, if down, increment z. Initially I took n and q as query, then I listed down all the coordinates over here, which is I comma 0, and I have marked head as the 0th coordinate. Then I'm reading the queries. If it is of type 1 query, I read which direction it is, and then I look at the current head and the type of character and replace it with the position of tail over here. And then I change the coordinate of head with tail again. And otherwise, if you are given a coordinate p where you have to insert like where this part is, like because my head is at position hd, so it's a zero based indexing, so that's why -1 over here as well. And like I try to find like where had you go add p coordinate to it, and assuming it's a cyclic array, so I take a modulo n as well and print those coordinate over here. Like any questions on this one before I move on to the next problem? Okay, moving to the next problem, D now. Problem D is again long and Takashi. It says there is a grid with n rows and n columns where n is odd, at most 45. Yes, I think we can use DQ over here, like where you remove the first element and add the last element. And like DQ would in fact be the better data structure to over use over here. Long and Takasi, there is a grid with n rows and n columns where n is an odd number, at most 45. So like this is important, odd number and 45. Let ij denote the cell at ith row from the top and jth column from the left. In this grid, you will place Takasi and a dragon consists of n square minus 1 parts numbered from 1 to n square minus 1 in such a way that the following conditions satisfied. Takasi must be placed at the center of the grid, that is at cell this. We don't have a choice over here. Except for the cell where Takasi is, exactly one dragon part must be placed in each cell. And for each x satisfying from x between 2 to n square minus 1, the dragon part x must be placed in cell adjacent by edge to the cell containing part x minus 1. Cell ij and kl are said to be adjacent by an edge if and only if difference of absolute difference of I and k and absolute difference of j and l is 1. Print one way to arrange parts to satisfy condition. It is guaranteed that there is at least one arrangement that satisfies condition. Like there are way too many conditions. Let's break it down first. Like the first condition says like Takasi must be placed at the center of it, that is at cell this. And like let's look at the sample. Here n is 5. So like center becomes 6 by 2, 5 plus 1 by 2, 6 by 3 by 2, 3. So like Takasi must be at coordinate 3 comma 3 4 5. So if we look at one of the possible output, like Takasi is at T, and except for the cell where Takasi is, exactly one dragon part must be placed in a cell. And we are also given the dragon part are numbered, there are n square minus 1 parts numbered from 1 to n square minus 1. So what it says is, unlike the previous case here, where like 5 and 1 were at the same point, we have to ensure that none of the part is at same point. So if we look at the example over here, like we are, since one part is at each place, here if you look at the example, like all the parts are printed over here and nothing is overlapping. There are no diagram over here, like I will show using a diagram as well. So like Takase should be at the center, and like in the example, the dragon is more like this. So like if we try to draw a dragon like this, what we can see is like all the parts would be continuous to each other. Like here would be the first part, here would be the second part, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1 second, like I may miss 14, 15, 16, 17, 18, 19, 20, 20, and so on. The coordinates like this. That's one way to do it. Like there are more ways to do it. Like for example, instead of starting from the outer loop, like like here we are not allowed to place it like this, like where the coordinates are like this. Here two coordinates will intersect for the dragon. Or we are not allowed to have like 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10, 11, 12, 13, 14. Like this is something like this is also not allowed because 5 and 6 are not near to each other. Like there are some points in between them. Like so like there are more ways to do it. Like depends on like how do you implement it. Like doing it like this is one way to do it. Like keep filling it. You can also start from inside like just like Takasi. You can also do some more patterns or try to do. Here the Takashi is. Like you can be creative, you can try to do drawings like this as well. Like as long as like the dragon is continuous to each other. So like these were the some of the ideas of how to do it. What I did was I went ahead with this pattern and I can show my code for this pattern. The idea is let me just create some 5x5 grid. Like if this is a 5x5 grid, Takashi is here. What I can do is I can greedily try to go right. If I can no longer go right, I will greedily try to go down. If I can no longer go down, I will greedily try to go left. If I can no longer go left, I will greedily try to go up. If I can no longer go up, I will again go right. So I start from here. As long as I can go right, I go right. Then I switch direction. I start going left. Now down, like right, then down. Now I cannot go down, so I go left. Now I cannot go left, so I go up. Now I cannot go up, so I go right again. Now I cannot go right because I will intersect with the spider or like snake again here. So now I change direction to go down. Now I cannot go down, otherwise I will intersect. So I go left, right. And this completes my pattern. Looking at the moving to code for this problem. Like in the problems like this, it's better to code directions like the x coordinate difference you want. So if I keep my x coordinate same and if I increase my y coordinate, it's essentially like I am moving right. If I keep my y coordinate same and if I increase x coordinate, it's essentially like moving down, assuming like 0 comma 0 is at the top. And if I am keeping my x coordinate constant and y coordinate decreasing y coordinate, it's like moving left. And if I keep my y coordinate same and if I keep decreasing x coordinate, it's more like moving up, like based on how your graph is. Then I have written one more function which takes x and y as the coordinate, and it returns true if it's possible to place some number over there. First, I am checking if x is between 0 to n minus 1, assuming 0 based indexing. Then I am checking if y is between 0 to n. If it's in q, then I'm also checking if this does not point still is empty. Like I initially marked all the points as empty by using -1 as a flag. And if I'm checking if -1 flag is still there, then I start with x comma 0 and I also maintain a variable dr for direction. I mark 0 comma 0 as 1 and a point p like that the next part where it should be. And I am running a for loop over here. Like I am checking if I can move in the current direction. If I cannot, then I change my direction to the next possible direction over here. Since there are 4 directions, I am taking it modulo 4, or you can do it some other way as well. And like when this condition is true, like not of this condition fails, so I come out of the while loop. Then I increase my x and y coordinate as required. I have also added an assert to ensure that this coordinate is empty. And if I have reached a Takashi's coordinate which is at t, I just put a break. Otherwise, I mark the current part at x comma y and increase the next part which I should have. Or also I have made pt less than equal to n square. So like ideally this condition should not wait. Then I'm running on all of my parts. If I am at -1 position, like I have ensured that -1 is only at the place where Takashi is. So there I would be printing t, otherwise I am printing all the x, like whatever the form I am. And this will essentially print like what was given in the sample as well. Like this algorithm will print this as the sample output. So like that's how I did D. Any questions on this one before I move on to the next problem? So like E is more like last due 3 Dijkstra problem which we discussed some time ago. du3 or du4. Yeah, probably it's a du4. Yeah, it's kind of similar to this problem. And like, let's read E problem again. Like, if there are any questions on D, I can take them off. You can put it in chat. Non-decreasing colorful path. There is a connected undirected graph with n vertices and m edges, where the ij connects vertex u1 and v1 bidirectionally. Each edge has an integer written on it, with integer av written on vertex v. For a simple path from vertex 1 to n, a path that does not pass through same vertex multiple times, the score is determined as follows. Let S be the sequence of integers written on vertices along the path, listed in the order they are visited. If S is not non-decreasing, the score of the path is 0. Otherwise, the score is the number of distinct integers in S. Find the path of from vertex 1 to n with the highest score among all simple paths and print that score. We are also given like, what do you mean by S to be non-decreasing? A sequence S1 to SL of length L is said to be non-decreasing if and only if Si is less than equal to Si plus 1 for all integers I between 1 to L minus 1. So like, let's see like what does the problem says. The problem first says that it's a connected undirected graph. So it means it's always possible to go from 1 to n. So like the case of like where there is no path from 1 to n is impossible now. And now we say like, if we take a particular path, if we list down all the score, if it's not an increasing like 1 2 2 4 4 5 5 6 7 points, like increasing, like let's list down some of the increasing sequence. Like this is increasing because like you can see like it's in the sorted order. It's not increasing because 4 comes before 2 over here. This is increasing. This is not increasing. And if our the order, if on our path the vertex on the index is like, if this is what is written on all the nodes on this path, then you can count the number, like it's first increasing, so the answer is non-zero. Now if we count the number of distinct nodes, it would be 1 2 3 4 5. If we look at this one, like on a path like this, because it's not increasing, our score will be 0. If we look at it, like there are 3 distinct values over here, 3 6 7, and because it's increasing, our score will be 3 over here. Again, here the path is non-decreasing, like 8 comes before 7. So in this case, our score is 0. So like what we can see is, we are given that it's connected. So the answer is greater than 0. Now like, so what we should try to do is, like if we have a graph from U to V, like we are given an undirected edges, right? What we can do is, we can create an edge from U to V. Like let's try to find a path which has all the nodes in the sorted order, because we know that if such a path does not exist, we can always print 0. If AU is less than equal to AV, and we will also add an edge from V to U if there would be an edge from, if AV is less than equal to AU. Or to make it more simpler, if AU equal to AV, we create an edge from U to V and V to U. Like from the initial undirected graph, we have came to a point where we are looking at a directed graph. If AU is less than AV, we create an edge from U to V. If AV is greater than if AV is greater than AU, we create an edge from V to U. Like these are the 4 types of directed graph we should create. And one thing we can note over here is, like if we travel on a edge like this, the number of distinct nodes will increase by 1. If we go on a path like this, like the number of distinct nodes will increase by 1, because initially you would be at AU and now you will go to a point where you have RAV and those values are different. And if you are at UV, if you go to AU, like the point increases, like the new point is different from the previous point. And because we are going in the increasing order, like your score will increase. But if you look at this path, like your score will not change because you were at initially at AU and now you are going to at AV, like that would be same, or the vice versa. When you are at AV, you go to AV. So now based on these conditions, 0, 1, and 2, like there were many ways to do it. Like one which strikes to my mind is one people can do 0, 1 BFS. Because notice that all the edge paths are from 0 to 1 and there is a directed graph. Like 0, 1 DFS would solve this problem. And I did a slightly different, I took a different approach over here. Like after you have not simplified the problem to this one so far, just copying a 0, 1 DFS code, something like this. Like just copying a code like this will make it get an AC where you are using some DQ or something. And I did a bit of different thing over here as well. What I did was, let's look at all the paths of where AU equal to AV for an edge. There is an edge from U to V, there is an edge from V to U. So what we can do is we can compress them into a single node over here using DSU disjoint set unit. So that any edge going out of U would also go to their complete path. And once I compress all the nodes like this, like my graph will no longer have an edges of form A equal to AV. So either it would be AU less than AV or AV less than AU. And then I can simply run a BFS algorithm or like something like that to find all the nodes. Where like I would be iterating on layer by layer. Like, oh wait, like zero, I just realized like 0, 1 will find the smallest path. But we need the largest path, like we want to maximize our score, right? So like we can do one more thing. We can first look at all the nodes which have value 1 on them. We can find the length of path from 1, 0 or 1 to all those nodes. Then we can look at all the nodes which are marked as 2, and we can like they must have edges coming from these nodes. So we can iterate on all of them, add +1 to it, and find the distance for all those such nodes. Then can look at 3, and we can try to find the distance for all of them. Like 3 can have edge from either node at distance 1 or node at distance 2, or 3 can have distance from 2. Like to summarize my approach again, like I first merge two nodes into one if AU equal to AV and they are near, there is an edge between U to V. Otherwise, if AU is less than AV, I create an edge from U to V. Like in my code, I am essentially doing the alternative U to V. Like, and if AV is greater than AU, you create an edge from V to U. Now, because you want to find the shortest node, you can keep all of these nodes and keep them in increasing order, process in increasing order. Where you take the distance of smaller nodes and try to find it. Like I will jump to my code for this one. Here I am taking everything as input, a DSU, like where I am merging all the edges which have equal points to them. Now I am changing all the edges to denote the leader of each edge. And if they are same like self loop, ignore them. Otherwise, if u is less than v, create an edge from u to v. I am maintaining a reverse edge over here from v to u. Otherwise, u to v. No, I doubt a DSU was necessary. Like there should be a way to avoid it. Like it just simplified my code, like so that I can avoid cases like this. Like otherwise, there would be a two-step process. First, you go to any node with same value, and then you try to do a zero cost path or something like that. Then it's distance, like a Dijkstra type of thing, BFS, like where distance and comma this is there and everything is there. Like now my PT are the shortest point. Like here I am adding all the points in a map, like for all the leaders of each connected component, because all the edges are between the root of each node in the Dijkstra. AU dot pushback B. So I am doing this so that I can iterate on all the nodes in increasing order over here. Now here I am iterating on all the nodes in increasing order. I look at the particular set and I find all the U where the node edge is coming from U to V. Like here I am maintaining the reverse edge. Then distance V is max of distance V comma 1 plus distance U. Because you have a direct edge from U to V, if you know the longest path from 1 to U, you can also find the longest path from 1 to V. And that would be essentially 1 to U plus a next edge. And you try all such nearby U's over here. And at last I check the distance of leader of n minus 1. If the distance is negative, like essentially I assign minus infinity, then it means like there is no path which has all the nodes in increasing order. In that case, we should output 0. So I assign answer equal to 0 and then I do C out answer. Like any questions on this one? Like there are around 10 more minutes for the stream. So I will try to rush for the next problems. Problem F is there is a row of n square labels 1 to n and a sequence a1 to an of length n. Initially, square I is painted black and the other n minus 1 squares are painted white. And a piece is placed on square 1. You can repeat the following operation any number of times, possibly 0. When the piece is on square I, choose a positive integer x and move the piece to square I plus ai in times x. Here you cannot make a move if I plus ai times x is greater than 1. Then paint the square I into ai times x as black. And we have to finally print the number of possible set of squares that can be painted black at the end of operation sum modulo. And if you look at the example, like it says there are many possible ways, like it listed down some of them. So like let's take this example. Probably I will move back to Zoom now. So like let's first take the first example. It says 1, 2, 3, 1, 1. So like first the square one is painted black. Like I'm using green color. Then what you can do is you can either stop over here or you can jump to the next coordinate. Like 1 plus 1 is 2. This is one possible way. Like from 1 you can jump to 2. You can jump to 3. You can jump to 4 or you can jump to 5. Let's suppose you have jumped to 1 to 2. Then 1, 2, 3, 1, 1 looks like this. Now these two squares are painted black. Either you can stop here or you can add +2 to it and you can jump over here, making this as a node as well. I will just use my mic and so like let's say if from 1 if you jump to 2, like 1 plus 1 2, and from 2 you can jump to 2.4 to 4. Either you can stop here or you can jump by 1 again. In that case would be. So like painting 1 to 4 and 5 is one possible way. So if you look at it, one way would be if you know the number of paths which ends at I, you can add this contribution to all the points j such that j is I plus x into ai. Like now, if you have dpj plus equal to, so now there are two ways to do it. One is at every point you iterate on from 1, you go from 1 to up till n, and once you know the dpi, you run a second for loop for each of the possible values of x and add dpj instantly. And the other way is you can notice that value of ai modulo aj, like j equal to I plus x times ai. If you look at this and take mod, then the value remains same over here. So other way is you can maintain a lazy order and square array, and instead of instantly going to all the possible j, you can create the dp sum array where you maintain ai and I modulo ai. Yeah. And then when you are at j, you iterate from all a equal to 1 up till n, and you are dp plus equal to dp sum a j percent a. Like I sorry for like convince, I was trying it for the first time. And like both of these algorithms independently will give TLE. But if you use both of the algorithms, like the second algorithm when AI is less than square root of n, and the first algorithm when AI is greater than square root of n, you would be able to get a time complexity of order n square root n. Independently, they are order n square, but this is combining both of them together with n if else would make solution order n square root n. Like that's often called as square root heuristic. And now jumping on to my code for f, like I will skip G for today. Like I have defined a constant R, it can be anything. I have taken everything as input. And number of ways to end at 0 is 1. Like it, I'm assuming 0 based indexing. And I also have DP sum array where like the k is of size k, so that I know for each modulo. Now from I to 1, I go over DP sum and add everything to the current value. Like that was the second algorithm. And if then I check the value of AI, like if the current value is 0 or if adding current value I jumps out of the loop, just continue. Otherwise, I take like how many points are left. So either if the current value of AI is greater than equal to R, or if number of the remaining points is less than equal to R, I directly iterate over all of them instead of lazily trying to find the sum later. Here I am directly adding the value to all the possible j. Otherwise, I add it into this lazy array where AI and I modulo AI as the sum, the current value, so that I can take all the values of those lazy values over here. And as I take all the sum of all the DP values and print it. So any questions on this one? Like this pretty much completes today's stream. Like I have a minute or so to take if there are any questions. I will skip this one in the interest of time. So thanks everyone for joining. See you again after Hello 2023. Like the one insight would be like the way I looked at it was to try to find primitive root, and for each number find like what power it would bring in the primitive root. And you know that something to the power p minus 1 for a modulo prime p is 1. So now each node will have some cycles when you multiply. Like if you have primitive root g, then if the current value is g to the power 5, then all you can have is g to the power 5, g to the power 10, g to the power 15, g to the power 20. And like 5, 10, 20 should be taken modulo p minus 1. So this essentially, like here you will see like the value would be like all the you can get all the possible values of GCD of 5 comma p minus 1. So like here like this you will be able to combine it. And then I did some smart ways. Instead of finding the explicit primitive root and g to the power x something like that, I did some more like you can read over here. Like primitive root is defined as like for every a coprime to n is congruent to some power of g. So for example, 3 is called primitive root of 7 because if you look at all the powers of 3, you will get all the values over here. Like there are some more algorithms, small baby leap or something like this, which can explicitly find the primitive root, but that were way like for the current constraints, they will get TLing. Like primitive root and discrete logs would be the two starting points. Like baby step, giant step algorithm is there. It's a kind of meet in the middle algorithm. You should probably read out these two algorithms first. They will not help solve the current problem because like prime is up to 1e13. Had it been 1e6, these algorithms would have given you the AC. And then try to use insights from them to solve it. So thanks everyone for joining. Let's move to code forces round.